All right, let's answer our discussion questions about the surface plate accessories. Make sure you're comprehending what you want, what's important when you're working with these. That's the point of these questions. So number one, how accurate were your Joe block stacks? What do you think of using these to check slots? And I'm quite happy checking slots with Joe blocks. I think it's a great way to check the full form and function of the slot with your go and your no-go. Uh, if there's an error, you're going to see it in the go side or the no-go side. And even with this part, we found there was a little bit of taper in one end, which still within print, but in a different part, you might see the go start and then stop, and the no-go might start and then stop. Either way, you have an issue. So if you're just going to be using calipers, you're probably only checking a few locations, and you might not check the entire feature with your calipers or other gauges. But the Joe blocks will check the entire feature, which I think is really great. And number two, what are the advantages of using the Joe blocks as a transfer gauge rather than using the height gauge directly without the Joe blocks? In that situation, when you're using the Joe blocks, you're really isolating the movement of the height gauge and getting rid of that component. So you're going from having error components from the height gauge and the indicator to the indicator and the Joe block. Excuse me. And we talked about how accurate the Joe blocks are manufactured. So the height gauge is going to introduce about 1,000th of error halfway through and 2,000ths of error all the way at the top stroke if you check what the manufacturers state their accuracy maximums are. So you really isolate that movement and lock it in place, and now you're just using pretty much the indicator deflection when you zero it on a Joe block. So I think that's a really great way to do it. And one of my go-to situations for a tight tolerance feature has a very small window, and I want to check the entire feature so I can slide my indicator all around that feature and have it zeroed on my nominal Joe block. I can watch the plus or minus and see if it stays in that window. Now, of course, we tested a few different ways. We tested with the Joe blocks and without, with the scribe and with the indicator, and they all have applications. As you use them more and more, you'll get a feel for when you want to use them for what situation. But I want you to be aware of what your options are. And of course, there are many more options than we went over in this training video, but these are the most common options. Number three, compare finding hole locations with height gauges and pins to using only calipers, which is more accurate, more useful, and quicker. So what I like about using the height gauge and the pins, for one, the datum surface that you rest on the reference on the surface plate, it takes advantage of the full surface. And if you're only using a caliper, you're only going to be grabbing it in one location. It won't be registered on the whole surface when you're measuring just one. And when you register on the whole surface and you flip it around and you run the other side, you can check for other things. Caliper would find that too. Check both sides with a caliper, but I like doing it this way when the tolerance requires it. It's not necessarily quicker. Sometimes it takes more effort than with the caliper. So with the caliper, it's great for open tolerance, quick holes, easy math. With the height gauge, maybe tighter tolerance, something with a true position requirement. And more useful. It depends. If you're going to be doing a lot of parts, sometimes setting up an indicator at a nominal height and then running parts through over and over again, it can be faster than grabbing the caliper and doing it over and over again. So it comes down to preference and accuracy, and look at your prints to help guide your decision. Which of the two methods in exercise 4 used to inspect runout do you prefer, and why? So let's take a look at exercise 4 again. So exercise 4 was the V-block runout exercise using a pin on the part or not using a pin and just going direct. So I like both. Personally, I do prefer using the pin when I can because as I explained, you can get a little more stability. Inside diameters, in my experience, tend to have more chatter, more taper, more issues than outside diameters. Outside diameters are a little easier to manufacture in many cases, so I like to use the pins, but of course it depends on the situation, what the datums are. So if the outside surface is a datum, then perhaps you want that on the V-block. If the inside surface is a datum, then you can slide it on a pin. It all depends, but I like both, and both have applications in metrology. Number 5 is kind of a challenging question. I don't have a good part to show this with, so we're going to walk through this exercise together. Consider the following 3 shaft parts made from the same design. So one design, we made 3 parts. We ended up with 3 situations. These parts are rested on a V-block on the larger outside diameter, so that outer circle on each part is the outside diameter. And a drop indicator is put on the smaller diameter, and then we're going to rotate the part 360 degrees. I'm going to watch the indicator because we're doing a run-out check. So for this exercise, let's assume the design is intended to have perfect run-out circularity position. So that would mean 2 circles machined right on top of each other, no form error, no elliptical nature like the first example has an elliptical nature. It's not off center like the second example, right? We don't want that. So how do you interpret each part as run out? How do you interpret it as position? And then as a tip, draw out each example every 90 degrees and what the indicator would show. So I've done that on some of these slides. Let's just jump into looking at the first one. And let me explain what's going on with this picture. So we have, in this first example, we have our part. I don't have the V-block shown, but each part is loaded in a V-block. And we have our indicator set to 0. And I put a blue dot to indicate the actual location where we set 0, so that when we rotate it, we can see where our 0 mark is moving to. So we set our 0, and then we rotate our part. And when that happens, we rotate 90 degrees. Now in this elliptical feature, it's caused the indicator to raise up and show more movement. So we've got a high point here, and we move on to the next rotation. We rotate back. Now the 0 mark is down here, and we're referencing 180 degrees from 0. And you see the indicator moves back from about 12, where it was a high point, back to 0 again, because this is a symmetric ellipse. And then we keep rotating to the 4th rotation. 0 marks here. We're back on a high point. We're back at about 12 thousandths of error, 13 thousandths maybe. So what we're seeing, if we rotate 360 degrees, we start at 0, we go up, we go back down, we go up, we go back down, and we're back at our 0. Those are basically the 4 positions or 5 positions that it sees. Now we compare it to the next example where we have a perfect circle, but one of them's off center from the other. So again, we set our 0 mark right here on the top of this surface and mark it. When we rotate 90 degrees, you'll see that the surface has raised up. It's definitely raised up, so our indicator has moved up. And then as we rotate it another 90 degrees, our surface has raised up again, so it continues to move up. And then when we rotate the next time, the indicator starts to move down, the surface lowers, so we're moving back towards 0. And then as we go, if we had one more to the right, it would look like our starting point. We're pretty much back to our starting point at 0. So the indicator, it starts at 0, it goes up again, it goes back down, and then it goes back to 0. But from your perspective, it's going to only show going up once and going down once, because there's no elliptical nature to it. It's just off center. And I do want to note, I have the indicator kind of drawn being off center line. That's just for the sake of arguing, for the sake of this example, like you're never going to see this much. This is an exaggerated example. So the indicator should always remain on center line. You can use a flat tip like I usually have loaded, and you'll see this with the flat tip. You'll catch all the error. You don't have to actually move the indicator off center line, but just exaggerating what's going on. And the last one, the last one I was just talking about, or I just had up. This is a combination. It's not only, it's an ellipse and it's an off-center ellipse. So what's going to happen when we rotate it? We start with our 0 mark, and then we rotate it 90 degrees, and we see it jumps really far, really fast, because we're grabbing an ellipse, right? We're jumping up. And then with our next rotation, it went up a little bit more, not a whole lot more, so we see a smaller shift in an indicator. With our next rotation, it's now starting to move back down again. So it moves just a little bit back down. And then with our last rotation, again, it comes back to 0, and it will move pretty quickly back to 0. So what are you seeing? If you do it 360 degrees without stopping, you're going from 0, it jumps up quickly, then it jumps up a little bit more, then it actually goes down a little bit more, down quickly, and then back to 0. So in reality, it's still just going up once and back once. This previous example went up once and back once, and our first example went up, down, in one rotation. So why, why is this important? Why would I want you guys to think about this? Oftentimes, when you're looking at shafts, the error that you see is really small. These are exaggerated. But when you're seeing error, what kind of error are you seeing? Are you seeing positional error? Are you seeing form error, where it's out of a circle and it's more of an ellipse? Are you seeing a combination? So if you're paying attention to what your indicator's doing, you can gain some insight into what's going on. And if you grab your micrometer or grab your caliper and you start going around checking different diameters at different locations, different radial locations, you can kind of piece together what's going on. But the indicator will help you in some of these situations when, and you may think, obviously some people think, well, if it's made on a lathe, it's never going to be off center. But with modern manufacturing, there's no guarantee parts are made on lathes anymore. Sometimes they're made on mills. Sometimes they're made on lathes and there's a work transfer that's off center. Sometimes they're made on mills and, there's a work transfer rotation that's off center. So you can't really take anything for granted sometimes. So your indicator will help you figure out what's going on. Let's make sure we've kind of gone through the whole exercise. Yeah, that's about it. We've answered what would happen in each situation, whether it's elliptical, whether it's a camshaft, or whether it's a combination. So just keep your eyes open and pay attention to what's going on. All right, number 6. What flatness check do you prefer? Pros and cons of each. I think raising it up on jacks, I think is what I prefer, but it is a little slower, as you see me demonstrate a couple of times. It takes some effort, especially when you have uncooperative parts, like this boy, like this one. So the shim check is great for a quick check, but if I really want a number, I am going to jack it up and run my indicator across. The shim check, again, works good on bigger parts that are difficult to jack up, or you need a quick check of how well you did it. But the shims, as I demonstrated in the lecture video where I talked about shims itself, there are limitations to where shims can reach and what types of errors they will see. But the indicator, putting it up on jacks, will allow you to check everything. So that's what I prefer. But they both have their uses. So that's it for me on this video. Thank you guys for watching. I appreciate it, and I hope you enjoy it. I want to thank the Laney Machine Technology College department, sorry, in Oakland, California. Let me use a couple of these parts for these demonstrations, and they have a great program. They have a great program for manual machining, CNC machining, metrology, CAD modeling, maintenance, grinding. I think they have a lot of courses. You can earn certificates in machining, metrology, and some other ones. You can get an associate's degree if you take enough classes. You even do apprenticeships classes there if you're working through an apprenticeship. And if you're doing any of that, you're really going to be setting yourself up in your career very well, because the industry really needs these people who have taken courses and gotten apprenticeships and certificates and degrees. That really goes far in your career. So if you're in the Northern California Bay Area, check out Laney College in Oakland and the Machine Technology Department. And please check out pragmaticmetrology.com for more of these training videos, more exercises, discussions about gauges, concepts that are important to understand, and resources that will help you. So I appreciate you watching. Thank you. See you for the next video.